Garcia. So her talk will be on the impact of dockless electronic scooters on urban infrastructure and impact on the public or transportation usage. Let me just give you a brief summary of Natalia. So Natalia obtained her PhD in civil engineering with a focus on transportation system at the University of Texas at Houston. And she obtained also a master in statistics and data science. And this is something that's very important to mention, like statistics is one of the foundation of data science. So Natalia used the statistic and econometric model, EE machine learning and stochastic method and simulation tool to understand the mobility and energy impact of new transportation technology, such as electric vehicle, connected and autonomous vehicle, and transportation network companies. So beside her academic work, she is involved in service and mentoring activity that promote STEM career to new generation. She has received 10+ competitive scholarship and award for research, teaching, and leadership excellence. Natalia is currently working at the Argonne Noun Laboratory. So I welcome you, and please go ahead and share with us your experience and expertise. Welcome. Natalia, can you turn on your microphone?
Can you hear me?
Yes.
Hello. Yeah, okay. Thank you so much. Thank you so much. I want to first thank you for the invitation. I'm very happy to be here, sharing my knowledge and my background, and hopefully to inspire others to pursue career in STEM area. My main focus is transportation engineering, so I try to use my tools, statistical modeling, and data analysis to find solutions to transportation-related problems. In this specific case, today I'm going to talk about dockless electric scooters, or e-scooters as we know them here. I'm not sure how popular are those in Qatar or in other countries. Here in the United States, they became very popular a few years ago, and because of that, they bring with them a series of issues and questions of how useful they are for the urban infrastructure environment. So today I'm gonna try to answer those questions with data. As I mentioned, the micromobility, or the small vehicle devices such as bikes and electric scooters, they experience an exponential growth with a faster rate of adoption than other forms of shared mobility. And when I refer to shared mobility, you can think of any transportation mode that is used by two or more people. So for instance, if you take an Uber, it's a form of shared mobility. With no current urban infrastructure design, electric scooters most share space with pedestrians, cyclists, and motorized vehicles. That causes a lot of different issues in terms of safety and other things that I will discuss later. But this is one of the main motivations of the study. But also, they offer alternative for short trips and are particularly suitable for solving last-mile transit problem. Yet its impact on transit is not well understood. So what I refer to with last-mile transit problem is that issue that deter people to use public transportation because they have to walk to the transit stop, and they have to walk from the transit stop to the final destination. And sometimes it is it's very an issue because people are willing to walk as much as 400 meters. That's on average. So if the transit stop is not within 400 meters, then they're not going to take transit. So electric scooters are seen as a solution to that because people can access and egress the transit system with them. But are they actually being used for that? So this is something that we're trying to understand and we're trying to model. So with this, the motivation of the study is the need to understand electric scooters demand patterns and user characteristics to develop adequate policies and regulation in the area. Research in micromobility has been focused mainly on bike share programs since electric scooters have been introduced recently massively. There's not a lot of research. The exponential rise of them have urged cities to rapid regulatory response. It's very difficult to regulate them in general. But now some regulation includes that data agreement, such as in the city of Austin, that this is very important because it allows transportation researchers to understand more of the usage of them and then to help to develop policies, but also has an issue that was also discussed in previous presentation of how data sharing can get into the privacy issues of the users. So there has to be a balance between the privacy, protecting the privacy of the user and allowing to develop analysis for this type of modeling. And in terms of public transportation and the role of public transportation, there has been and some research indicate that the more people use share modes, as the ones I mentioned before, Uber, Lyft, and electric scooters, the more likely they are to use public transportation, public transit, because they're just out there using the public transportation modes. But the truth is the transit ridership in the US has been flat or declining over the past few years, and there's a debate whether of these modes are as a supplement, feeding the public transportation, or as a complement to public transit. Therefore, more research is needed to understand the actual route of the public transportation, and then data. Data is very important, but sometimes it is very challenging. So finding spatial and temporal relationship, dealing with computational complexity, and the integration and fusion of several sources make it very difficult and very challenging for transportation engineers to develop solutions. So with that, I just want to summarize what my main motivations are. The impact of electric scooters in urban areas is still unknown. There is not clear understanding what is the effect of electric scooters on public transportation, and the data, when available, may present several challenges. With this, my presentation today is going to be about design and applying models and methods to evaluate the impact of different aspects on different aspects of urban areas using data analysis techniques and data from electric scooters in Austin, Texas, specifically, where I did my PhD, and this is part of my PhD dissertation. So first, I'm going to talk about what is the impact of dog leg. For this, trip trajectories are very relevant to understand the use of the current infrastructure and trip making behavior. Now, the data standards, as the ones I mentioned, the data regulations I mentioned before, they allow to the multiple data analysis and comparison across cities. However, it is limited in terms of what type of information can be provided, and therefore is limited of what type of analysis can it be provided. So we evaluate the integration of electric scooters into urban infrastructure area using trip trajectory from an electric scooter provider company while preserving data privacy. So right now, the data standards do not allow to share data trajectories because it is such a granular level that can be used to identify a person. But what we're trying to do here with we sign a data sharing agreement with this company and trying to find ways to analyze the data so that we can provide useful analysis for regulation, but also protect the user information. So what is the best way that providers can use to share data so that we can still use it and also provide protect that user information? So for this, we use data from 1 year, specifically from March 2019 to February 2020, before pandemic started, and that provided in this time were about 80,000 trips, and there were 5 million trips in the city during the same period. So what we have is a sample from a specific provider in the city, but also we're using urban infrastructure information, sidewalk, bike routes, and roadway GIS information from Texas Department of Transportation roadway inventory. And what we're trying to do is trying to find which what is the infrastructure that the users are using? Are the scooter users passing through sidewalks, bike routes, or roadway mainly? And how speeds change across these three urban infrastructure data? So what we did, basically, we use GIS data to estimate areas covered by different infrastructure assets that I mentioned before. We estimate some buffer width and using the information of the text.roadway inventory. And then with using that trajectory data, we determine speed and define some ranking methodology so that we can assign that this person was passing through this specific urban infrastructure. The main goal was to trying to find what type of data aggregation can be used by the providers to distribute information that is not at the level of trajectory, but that can be useful. So here I'm showing an example of how a map of the urban infrastructure look like in downtown Austin. We can see the roadway functional class is the type of roadways that are available, interstate freeway, principal arterials, but then we can also see the sidewalks and bike lanes across the area. So what we're trying to do is using all trajectories that we have and trying to identify where are users passing through with some GIS processing, we were able to find, this is an example of a trip with a percentage of 2% in sidewalks, 43% bike lanes, 20% on roadway. This is very important because then this is just one trip, but now imagine we know what is the distribution of these trips across the city. We can know which infrastructure is mainly used by users and what is the speeds difference. So that's another question that we wanted to ask to the data. So this is an example of a mainly sidewalk trip. The user was 60% sidewalk, didn't use bike lane, and used roadway 22%. This is very useful, but we still, so just to clarify, this is a trajectory, but we still anonymize the origin and destination so that no one can track the person. But overall, what we want to understand is some distribution. So I'm having here the distribution of the trips, of the speed of the trips of those segments within sidewalks, bike lane, and roadway. And one question that we're asking here to the data is the speed in the urban infrastructure the same across them, and also is the same during different times of the day? So for that, we use an analysis of variance and a statistical method to be able to answer if the means are the same, if the mean of the speed across all these infrastructures are the same. The analysis and results suggest that not all the means are equal within infrastructure type. What that means is that the speed in some the speeds are different. For instance, we found that the speed of riders on bike lanes is 9% higher than in sidewalks and 7% higher than roadways. This is important because this is saying that users are more are likely to ride the electric scooter faster on bike lanes, but bike lanes are not made for electric scooters. So with this information, what we can do is trying to find a way to regulate or to encourage. What do we want to do? We want to have electric scooters in bike lanes or in sidewalks. In sidewalks, we can see that they are slower. In roadways, they are also slower, but it's dangerous. So this type of questions and this type of analysis is what we need to develop some policies in the future. And thanks to the data, we're able to do that. But as I mentioned before, there has to be a way for the provider to summarize this information in a way that it also protects the information. In terms of other results, we didn't find a difference across time of the day, but yes, across infrastructure. With this, some summary of this part of the analysis is that the GIS analysis and the statistical techniques were able to solve some transportation problem. It can be used to inform future electric scooters right of way and speed regulations, and the integration into the data sharing standards can be useful to preserving cycle information while also protecting personal information, and further collaboration within entities responsible for collecting and maintaining data and infrastructure data is important. So as I showed, the infrastructure data was the main source of where we were able to do the analysis, but sometimes this is not very well maintained and very well accessible. So we want to encourage that entities can have better infrastructure data so that we can do better analysis. And another brief analysis of micromobility in terms of the impact of transit use. We want to determine the relationship between electric scooters and transit trips, and this is very challenging. For this part of the analysis, I'm going to try to evaluate the use of electric scooters and transit as a last mile solution to determine if electric scooters serve as a complement or as a supplement of the public transportation systems in Austin. So for this, I am using the data that is openly available in the website of the City of Austin, and this time I'm just using origin and destinations, but I'm also using transit boarding and alighting. That is also information that is shared by the transit agency in Austin. So what we're trying to do is, and this is part of an, I'm not going to talk about the review preference surveys, but the data that we have, it's very useful, but again, we have a lot of data, but what can we do with this data? So this is the part of the data scientist contribution that I did of the part of the analysis. So a summary of the data is we took about 84 days where the unit alpha analysis are count of electric scooters within 50 minutes intervals in 51 areas of study, with a total sample size of about 70,000 per area. And determining the relationship between electric scooters and transit can be challenging because of multiple confounding variables. And a confounding variable is a variable that affects both dependent and independent variables. The current literature in micro transit does not address this modeling issue. So imagine you want to determine what is the effect of the count of trips in electric scooters with the count of trips of transit. When you just think of a linear model, there is going to be a direct correlation between these two variables because of evident confounding. And when we try to do this first with the spatial error model, we found a strong correlation within the two variables. But the question is this correlation actually because the people are using electric scooter to access transit? The answer is no. This is not the best way to model. So for that, we developed a methodological framework. It consisted of two regression analysis. The first regression analysis consists of a quasi-experiment. We separate the variables that can be explained by the confounding variables from those that cannot be explained using a gradient boosting machine regression. And this is a machine learning non-parametric method that allows to model nonlinear data. And it's highly used in different modeling that is very tend to be very accurate. So that's what we wanted to use it. So this first way, in this first model, what we're actually trying to do is to model as good as we can these two variables to separate whatever effect of the confounded are within the two of them. So with this we develop metric called the ratio transit intensity, and then this phi, which is gonna tell us what is the ratio of transit alighting trips versus what's expected in transit trips given the confounding. This is important because, for example, if we have 1.2, a phi of 1.2 means that bus alighting trips are 10% higher than expected. With this, we come to a second model when we are now able to isolate whatever variance is not explained by the confounding, and then in this model is we were trying to explain the actual last mile behavior. We use, because it's in terms of counts, we use a negative binomial, but because we have several zeros, we also, for checking for confounding. We use a zero-inflated negative binomial model. These are summary of the results, and I'm showing in the gray area the results that are non-significant, and in the color area the results that are significant at the 95% confidence level. And the two models are just a way to prove the robustness. How to interpret these results? We can say that when P is 1.1 or the boss alignments are 10% higher than expected, electric scooters in trips can increase about 2% at the UT Austin area and around 3% in the downtown area. And we can see this effect keeps constant in the area when we use a negative binomial model, which kind of corroborate a bit of the robustness of the method. But what we're seeing here is how the developed methodological framework was able to model last mile and to detect some statistical significant effect between electric scooters and transit. But you can see that the effect is very small, is very minimal, and is only present in the university area, which is located here in this area, and in the downtown and in some residential areas, mainly students and some commercial areas. But with this, what I want to say is that the developed methodological framework was able to detect where and how, but we can see that the effect is very small, is very minimal. With this, I just want to summarize. In this part of the analysis, we made a application of a machine learning technique to a transportation problem. The method that we developed can identify areas with potential electric scooters and transit interaction. But mainly, it's important because we need to recognize the significance of electric scooters and transit interaction in order to be able to help the city to develop appropriate policies and measures to either incentivize transit users, to understand the role of electric scooters as a complement or as a supplement of transportation services. And then the developed last mile models can further assess this relationship in other locations and can be adapted to different rideshare modes. So we can also apply this method to bicycle, bike share, or TNCs. If TNCs are referred to Uber and Lyft system, are people actually using Uber and Lyft to access transit? So that's another question, another very important question that we're trying to answer. But this methodological analysis can help solve some of the data issues that we encounter for other modes. With this, I just want to thank you. And if you have any comment and question, you can either put in the chat here or email me directly. You can also visit my website or some of my social portals where you can check more from the research papers I do, or like just email me or have some questions. I'm happy to answer. Thank you so much.
Thank you, Natalia. Thank you very much. This is another view of how we can use, all this background, statistics, mathematics, computer science into data science, but this is looking from another point of view. So to answer your comment at the beginning of the talk, yes, here we have e-scooters at Qatar Foundation. Qatar Foundation is it's like a small city, but it's an education city, and we have plenty, and we are expanding this to the city of Doha. So this will be a good, probably we can try this model using your expertise. So there are a couple of questions. One question that's a little bit overlapped with what I was going to ask you. When you were using the first statistical model, the ANOVA model, you used the you were comparing between the weekdays and weekend, right? To see if there is any statistically significant difference. I was wondering if there is any, did you include or a confounding factor which is related to the gender and age? Because we know that the e-scooters is probably will be used by young people, by students more than probably old, like someone who is 60 or 90 because they are scared of falling down. So did you include those as confounding? And also probably girls will not have the the flexibility, or I mean the freedom probably to use it as boys. So this is one question, and I have two other questions that will come. But
thank you so much for that question. So since what we obtained from the provider was trajectory, we don't have information about the user. This is what I mentioned was important because they always try to keep the privacy. And in both of the data set that I show, we don't have information about the user, but I didn't, because of time, I didn't include the survey that we did at the university, which we actually tried to capture this user information. And as an important point of what you mentioned, like the difference on sex and ages. Of course, because our study was made at a university, but the majority were young people,
Yes.
but the university was the highest hotspot in the city. So in terms of the sex differences, the literature suggests that electric scooters can close gender gaps because there's a lot of gender gap in bicycle use. For instance, many women do not like to use share bikes because of different factors, like even the way the dress, like how you dress, affects how you can ride a bike. So
Yes.
some research suggests that electric scooters can help close that gap because then it is easier for a woman to drive it. But based on what we found in the university survey, we found that this gender gap is still present. So it's not solving what some researchers were suggesting, that the gender gap will be closed with the electric scooter. So yes, we still have some gender gap in the use of these vehicles. Unfortunately, I cannot model that because of the data issue, but it is important to mention that.
Second question, could you please explain what is a quasi-experiment as you are using observational data?
Yes, thank you so much. So a quasi-experiment is when you're doing a causal analysis, you sometimes want to have the perfect conditions, as in like what would happen if I don't use this and what will happen when I don't use this, the two scenarios, let's say. But sometimes you rarely can have perfect conditions to test two variables, let's say. So in general, what a quasi experiment is when you try to simulate situations. So for instance, in here, what we're trying to simulate was the separation between electric scooters and transit. So you can think of a quasi experiment is like a in the data you try to simulate conditions as you would do in the real life, but you cannot do that in real life. But
Yes, I see. So one last question, since we have 1 minute. I'm curious whether the portable nature of e-scooters make their end-to-end trip time more consistent compared to cars. That's a little bit philosophical question because they are light, etc. by comparison to big car, especially that here we have like a big car. So
I'm not sure I understand the question because they're portable and can compete with vehicles, or like, can you repeat the question?
So I'm curious whether the portable nature of the e-scooters make their end-to-end trip time more consistent compared to cars. I think probably because it
Okay,
is
because you can just leave it anywhere, I guess, because you can just leave it
probably
anywhere. You can,
yes,
it's easier than a
then a car
vehicle.
with
Yeah.
a part.
Well,
Yeah.
it may be, yes, because because you can just leave it anywhere. Like most of these dockless electric scooters, you can just finish whatever you can, and if as long as you have space to locate it, you finish your trip. But one important factor here is they're mainly used as for short distance trips. Your vehicle, you can just do very high distance, but so yeah, they can be more competitive than vehicle if you're talking about a short distance. But when we have long distance, there's not the case, unfortunately.
Yeah.
And
Maybe
just one question there, that what happened with Longhorn football? I don't know. They're doing very,
exactly.
very bad.
So yeah, so I have other questions, but probably I will just share them with you offline. So
Yes,
that
sure.
will not go beyond the people maybe are tired, etc. So thank you very much, Natalia. It's a pleasure to meet you. And coming from a statistical background, it was very very nice to listen to your talk. So good luck with
Thank you.
experience. Thank you very much.
Thank you for the invitation. And if anyone has more questions, please feel free to email me. Also, I'm happy to have a talk or anything. Thank you so much.
Thank you so much, Natalia. Thank you. So with